Hello, this is Ms. Nichols, and this video is on conservation principles and systems. The essential question that you should write down in your notebook is, how can I use open and closed systems to track the flow of conserved variables over time? What are these systems and why would I care about them? Okay, so conservation principles are some of the most important critical concepts in physics, and they really control a lot of what we can do in science because certain things are conserved and other things are not. The word conservation means to keep the same amount of something over a period of time. As far as physicists know, in this universe, there's actually only 6 things that we actually have the same amount of all the time. So 6 things that are conserved in our universe. That means there are 6 things that cannot be created or destroyed. They've been here ever since that moment of the Big Bang, and we're going to have the same amount of those 6 things into all eternity. Those 6 things are, number 1, mass. So all of the mass of the universe is never changing. We've always had it, and we always will. A variable called momentum, which you may have heard that word before, but momentum is also conserved. Another variable called angular momentum, which has to do with spinning objects. Energy, so energy is also conserved. Something called charge, which happens inside of atoms. We have electrons and protons, and the charge of those things is conserved. And then also the spin of subatomic particles. So those are the only 6 things that are conserved. That means all the other variables in the universe, velocity and acceleration and time and all these other things are not actually conserved. Those things are changing day to day. So when physicists are trying to figure out what's happening with our conservation principles and variables that are being conserved, they often use a tool called a system to help us separate objects from the rest of the universe so that our analysis is simpler, because this is a complex area and we only want to deal with a few things at a time. So physicists will, in their brains, kind of draw a box around an object, and that box keeps everything else out and only makes me analyze the stuff that is inside. And so that imaginary box is called a system. Now, we can draw real boxes around things to show our thinking and to show what kinds of systems we are including. And there are 2 kinds of systems that you will be encountering over the course of this class. We'll be drawing them differently, and I'll be giving you details here in a minute. But so if I was interested in analyzing this block of wood and those nails, I could show that I'm including it in a system by putting a box around it. Maybe my system is more complicated, like this entire car and all of the stuff that is in that. I can make that car into a system and separate it from the road and from the drivers and from everything else by drawing a box around it as well. You'll notice I use dashed lines in that second box. That's a different kind of system that we're going to be going into the details in just a slide or 2. So the first kind of system that you should be familiar with is what we're going to call a closed system. And as the word kind of indicates, a closed system assumes that we are totally going to isolate our objects from the universe. They are all by themselves. Nothing else is touching them. Nothing else is acting on them. Nothing is going in or out of our system. The stuff inside the system can still be moving around. So we can move around inside the system, and it may even look different at one moment versus another, but none of it is allowed to disappear, and we're not allowed to add anything to that system either. So for example, that system we saw last page, which was a block of wood and some nails, maybe we have that labeled as, this is what this stuff looked like 2 days ago. Because it's a closed system and nothing is allowed to go in or go out, all that stuff has to stay in the system, but it can change shape. So maybe after a little bit of time and effort today, it looks a little different. Same block of wood, same nails, but today it has a different shape. The shape is a birdhouse, and then there's like a pile of sawdust because I had to cut some things as well, and I had to keep everything in that system. I wasn't allowed to throw away anything or let anything escape. So this is the same system, the same objects isolated from everything else, and they have changed size and shape over time, but nothing has gotten out or come into my system. All right, so how do we tie together our idea of conservation with our closed systems with some of the variables that we've learned? Well, by definition, if you're conserving a variable, you're keeping the same amount of it. That means the sigma, or the total value of those conserved variables, should not ever be changing. So if we have a closed system for mass, the total mass, or the sigma mass, is going to be the same whether we're talking about it yesterday, today, or 2 years from now. So if we go back to our birdhouse situation, maybe 2 days ago, we actually got a scale out and we measured. We had exactly 3 kilograms of wood and we had exactly 1 kilogram of nails. I don't care about those individual values, but what I do care about is knowing that the total for the system, the sigma mass for the system, is 4 kilograms when I added those together. And the reason I care about that is because mass is conserved, which means today, after I've made my birdhouse and I measure the mass of the birdhouse and the mass of the sawdust, maybe I find 3.5 kilograms of birdhouse and 0.5 kilogram of sawdust. When you add those guys together to find your new sigma, it better be the same value because mass is conserved. So when mass is conserved, we're always going to have the sigma mass stays the same in a closed system. How about delta mass? Remember, delta means the change in a value. So if I look at that mass, it started at 4 kilograms total. It ended at 4 kilograms total. Hopefully you can identify that the delta or change is 0 for this system. We had 4 kilograms at the end. Take away the 4 kilograms at the beginning. We didn't change at all. So conserved variables in a closed system, sigma will always stay the same, and delta will always be 0, showing that the variable is conserved. So the other kind of system that you may find yourself wanting to use is called an open system. You would choose to use an open system if you had a more complicated system, because in an open system, we allow things to move in and out, even those conserved variables like mass and energy. It is important to remember that that doesn't mean the mass and energy are being created or destroyed. They're just moving from one open system into another, and in the universe, they would still be conserved. So for example, this car is more complicated, so I'm going to draw an open system around the car, and I show that by using a dashed line, which is kind of like lets stuff in and out. And then I'm going to think to myself, which variables are going in and what variables are coming out, maybe over the course of a day. So in the course of a day, people might go into that car, so I'm going to show mass of people going in. Gasoline might be put in the car, so we have energy of gas going in. Things are going to come out as well. Smoke comes out of the tailpipe, so that's mass leaving the system. Maybe rubber comes out of the system because the car squeals out at a stop sign or something and leaves some rubber on the road. And energy might come out of that system in the form of heat, for example. So this is a good system to handle with an open system because we have all of these conserved variables, but they're really hard to track. They're moving in and out of the system. So as far as tracking the variables in open systems, delta is much more useful than sigma. Sigma is changing all the time. So usually what we're interested in an open system is the delta. The idea is that the total amount of mass and energy in my system is changing over the course of the day. I usually like to categorize this change into positive deltas and negative deltas. So remember that positive means these things are going in or added. We are increasing the mass or the energy of the system when we put people and gas in. And then we've got negative deltas for things that are coming out of my system. At the end of the day, you might want to know how has the mass or the energy of the system changed overall. And it's a pretty straightforward process, right? We're going to take all the masses going in, like people, and subtract all the masses that came out, smoke and rubber, and then we'll get an overall delta M for this car, and we can talk about whether its mass went up or down. If you have a positive overall mass, delta mass, or a positive overall delta energy, it means that the car gained some over the course of the day. And of course, if you end up with a negative value, that means that the mass or energy of that system is going down. You could, of course, also end up with a 0 value. It would be sort of a random coincidence in an open system to get a 0 value, but it could happen. So imagine you're trying to solve a physics problem. There's no one right answer to what kind of system or what objects to include in the system you should always choose. In fact, one of the skills of being a physicist is choosing a system that makes your life easier to solve a problem, but there's not only one way to get to a solution. There might be multiple systems that are going to work, and you're going to be the one that's in charge of choosing which systems that we use. Typically, I would try to choose a closed system if you can, because we can use those conservation principles in closed systems. It's a law of nature that mass and energy are conserved in closed systems. So if you can imagine keeping track of all the stuff, it's going to make your life a little bit easier because you can use those laws of nature. However, You got to keep in mind that sometimes variables change the way they look or change the way that they interact with things, and so it can be a little tricky to keep track of those variables sometimes. Open systems, on the other hand, are really useful when you have something much more complicated. When you know you're not going to be able to keep track of all of the little bits and pieces and parts, then you might choose to use an open system. But the downside is you don't get to use these handy-dandy conservation principles. You can't say sigma mass is staying the same if you're going to be dealing with an open system. So you get to pick. Both kinds of systems have pros and cons as you move forward. Okay, we've reached the end of the video. Please take a moment to revisit the essential question, write down a summary or any other questions that may have come up for you or any other ideas or anything else that's going on. How can I use open and closed systems to track the flow of conserved variables over time? And then pause the video and take a minute to recap and pause. Thanks for watching.